Well, hello, Sky Protocol community. This is Gauthier, and today I am with Fare. Hi, Fare.
Hello.
All right. As you can see, we have two beautiful microphones. Um, we don't really want to spend all of our budget in marketing stuff and in trinkets that make us look neater, but I know that it's more comfortable for you guys to listen to our code updates with better mics. So, from our own pocket, we bought cheap microphones, but be assured that we hear you. We know that microphones are an issue, and so when we get some level of funding, something that is satisfactory and that doesn't give us a sense of perpetual emergency, you will know that because we will buy the most luxurious microphones. We will buy like classy Rode Procaster microphones and so on, and even the XLR mixing table and everything. But so far, we have at least something better than the ambient microphone from the computer. So today we're going to have a little code review. Yesterday we had the video that was dedicated to responding to all the little questions about the architectural concepts of Sky Protocol. Here, Farah is going to comment pieces of our code and, of course, the most recent ones. And next week, we're going to have our developers show their faces and comment their own code. One of them is not going to show his face. He wants to keep his privacy. That's life. So he's just going to make a voiceover to comment his code. And another one is going to do that full face so that you guys can see a little bit more members of our team. All right, so Fare, the stage is yours if you want to share what we've been up to for the past weeks.
So recently we focused on two fronts as usual. One is a contract and the other is a server. The main thing on the contract, we are merging it right now into the main repository. Like it had its own repository because it was experimenting and doing lots of things, but now we are merging it in the main repository. It's currently in a branch called contracts in the main repository. And the node surprise was being rewritten in Haskell instead of Scheme because we had reached a good stage in Scheme, but now we wanted to take advantage of some parts of the ecosystem rather than reinventing them. So we had it was a painful decision. Like there are some things that are much better in Scheme, but other things that are better in Haskell, and we decided to go for reusing the code from the Cardano ecosystem. So here we are, and the Haskell code is in a branch called issue 12 or something. And so right now I want to focus today on the contract because that's a part that is more fleshed out and more interesting. And so maybe I should share my screen. It's useful. Share screen, entire screen, entire screen. How do I do that? Enter. Okay. And now you should see that I'm on my Git checkout. And the Git is in a branch called contracts, and it's a subdirectory called contracts. And here we have something that started as a copy of some Plutus template or Plutus generic repository that we copied and forked and added things. And the interesting things in there are under the directory called src. So let's go in src. And basically, we have three contracts. Trivial contract, the Sky minting policy is to create an NFT, and the NFT is used to track the state of our bridge contract. So you may or may not know this about Cardano, but it's a UTXO-based blockchain like Bitcoin. And how do you write contracts that have more than one step, or that keep living and that must be seen by other contracts? The way you do that is that you create an NFT that identify which is the state of the contract. So whichever UTXO hold this NFT owns the contract or represent the contract. And so that's what the Sky minting policy thing does. It's a very trivial contract copied from other contract with minimal modifications that just creates an NFT, a unique token that identifies the state of the contract. And then with this contract, so there's not much to see there. I'm just showing you where it is and what it looks like inside, but it's not very interesting or very original. The thing slightly more original is the bridge contract. So it's a file called Sky Bridge Contract. And so this is where more of the magic happens. And here we define things like a hash or a public key or a list of data operators, a multi-sig, a very simple multi-sig. And all that we use, then we make it available to Plutus. And then the Plutus NFT datum is basically a hash of the state of the contract. So we don't put the whole state of the contract on chain. The whole point of putting things off chain is that we want to minimize the amount of on-chain state. So it's as cheap as possible to update the things that are on chain, while most of the work happens off chain. So these contracts basically contains a hash, and the parameters are basically the NFT currency symbol. That's not very interesting. Here, bridge redeemer. Okay, so to update your bridge, you depend on having a multi-sig pub key that you will reveal, and the old data hash, the old state of the bridge, and the new state of the bridge, and the signature that the transition is correct. So basically, I'm going to reveal, here is the multi-sig that I'm using, and here's the signature for that multi-sig, and here's the data hash, the data of the chain. And I'm going to verify that the old state basically is a hash of those two things. And then I will replace the new state by this, and then that the transition is correct if the signature fits. So basically, this identifies who is a committee. The signature said yes, the committee said that the transaction is correct, and this is the old data that was held by the bridge, and this is the new state of the bridge. So this is the bridge basically allows one thing, which is update the bridge. So the contract is very simple. There's very little that can go wrong in the contract itself. The thing that can go wrong is if the committee gets hacked. So that's a usual problem with if your chain gets hacked, but that the contract itself will be solid. There's no leeway in the contract itself for breaking. The leeway for breaking is if the network protocol code outside the contract fails, which we're working that it won't happen. But the contract, the goal of a contract is to be as simple as possible so that there is as little space for a hack as possible. And this contract is really so simple that it's impossible to get it wrong, or the thing you could get wrong is if you don't do the multi-sig properly, for instance. But this is a very well-known, very simple problem, relatively speaking. Simple in the sense that the people who designed the algorithm did something very complex, but the algorithm is well-known, and we as implementers only have to reuse the algorithm correctly. So there's very little room for getting things wrong in this contract. And so here is a simple code to find the current UTXO. So basically, we are going to find this the UTXO that has that holds the token, and then we can do things with it. And all the rest is just doing. This is just Haskell code that does exactly what we said. That is verify that. To update a bridge, we must verify that the signature is valid and that the output has a proper NFT, and the NFT is updated to have the new top hash, and that the old top hash matches between the committee and the old data hash. So this is what I like, is how simple and nice it is. Okay, so now the next question, the rest, multi-sig verification, type validator. Okay, so you can read that code. It's designed to be dead simple. That's the beauty of smart contract design. If your contract is complex, probably you're doing it wrong. Because the contract has to be rock solid, so simple that anyone can audit it, and it should be that simple. So the fact that it's relatively simple and not complex is a feature. It's desired. Okay, now here's a simple client contract. So having a bridge is nice. The bridge updates the state of the chain of Sky protocol so that things on Cardano can see the state of Sky protocol. But now, what can they do with the state that they see? And that's where you can have things like this bounty contract, which is an example client script. It's a client that will read the state of Sky protocol and verify that something did or did not happen on Sky protocol. So the whole point of a bridge is that the bridge contract updates the state, and the client can now see what's happening. So did you publish the data that you promised to publish? Is your side chain, you have a side chain and you claim that the state of the side chain was publicly visible for anyone to see to avoid data availability attacks. It is the whole point of Sky protocol, avoiding data availability attacks on very large volumes of data without publishing this large volume of data on Cardano, where Cardano is limited to 4 kilobytes of data per second total. So you want to publish 1 megabyte, 1 gigabyte of data, you publish it on Sky protocol, and then Sky protocol updates its state, and then you can see was the thing seen on Sky protocol, and the answer is yes or no. And to prove that it's been visible on Sky protocol, here's how you do it. So here's a bounty contract that will pay you something, a very simple contract, the simplest client contract. Someone will pay you something if some data was published on Sky protocol. And instead of paying you something, it could be instead validating an update for a sidechain or something like that. But here it is a simple bounty thing. So the params are you will receive some bounty and and you receive this bounty if you can prove that data of the given hash was published on Sky. Okay, so this is a bridge contract initiative. So this is the okay. The bounty that you receive will be any asset attached to the UTXO of the bounty contract. So the bounty contract, the beauty of it, it's so simple. It does not have to know about the exact asset that you will receive as a bounty, because this asset is implicit in the fact that it's whatever asset is attached to this bounty contract UTXO. So once again, keep things as simple as possible, because then there are fewer things that can go wrong. And in a world where people try to hack you, you want as few things as possible to go wrong, or to be able to go wrong. Back when I was at Google, they had this thing, "Don't be evil," that was later canceled. And my theory is it's a canary. That means it was Google said that as we haven't done anything evil yet. And when they removed the "Don't be evil" from their company motto, it meant that now we have done something evil. We removed the mottos, and we're not allowed to tell you what we did, what evil things we did, because the government forced us to do it. But at least you know that we did something wrong. Well, our motto in the cryptocurrency businesses is more like, don't make it impossible for us to do evil. It's not "don't be evil," because some forces will come to try to corrupt you. And in the cryptocurrency business, we want to say, well, yes, people will try to corrupt us, but the code is such that they cannot corrupt us. Even if we wanted, if we were accomplices, they cannot make us do it. So we want things to be really so simple, so solid, so transparent that it's impossible to do wrong, making the wrong things impossible. So the parameters of this contract are simple. It's just referring to which bridge contract we're talking about. Well, we want to see something on this bridge contract, and what it has to see is that on this bridge contract, we saw this hash. And in the future, we can add more things. We must saw this hash before this timeout or something like that. We can change that in the future, add more complexity. This is just a simple example of how you do a client. Okay, so redeemers for client contract. Now the redeemer, that is the code that, okay, this has a parameter of the contract itself. The contract has this tell you which bridge referring and what it wants to see on this bridge. And to check that this thing was indeed followed, now you need to provide a Merkle proof that the data was on the bridge and a multi-sig pub key hash. This is revealing the pub key of the bridge. This is basically a proof for the top of the Merkle proof. Basically, that's the argument that the thing you see in the Merkle proof is a series of hashes that prove that the data was included in a tree, and this is a proof that the top of the hash is a thing you expect. So you will basically compare this to the. You will use this to compare the top of the Merkle proof to what's in the bridge contract, and then you will check the Merkle proof that checks that indeed it's a proof that your data has been included in the state of the DA of the data availability network. So, okay. So how does it work? You can claim the bounty if it's a valid Merkle proof that basically you extract the target hash and the NFT symbol, and you want and the multi-sig. Okay, you take this. You take the Merkle proof and take the Merkle proof here. You get the NFT bridge data from the context, and if you can't find it, it's an error, of course. And if you find it, then you check that the Merkle proof is valid, and you can go down there, and okay. So you verify that the top hash is indeed the top hash you want, and the target hash. Your target hash is left or right. Yeah, this is a simplified, very simplified Merkle proof, because this is the current state of this code. This Merkle proof is trivial. It's the tree is of fixed size 2. You can only have 2 data in the data layer. We're totally taking this is mocking. We're mocking it up. Like we are working. Yaroslav is right now working on making actual Merkle proofs that are less trivial than that. But since we had to issue the contract as fast as possible and show that the important part of the contract is all the rest, is all the structure of it, all the boilerplate, if you want, all the architecture of it. So all the architecture of it is here. There's an algorithmic part that's not here yet, that we're working on it this week. And we'll have it as soon as we have it, but the architecture is there. So all the big picture is there, and in the small picture, indeed, a simplified Merkle proof is a bit oversimplified. That's fine. That's on purpose. We decide what are the things we can. This is a known problem. Writing Merkle proofs is a known problem. I've done it in Scheme. We're doing it in Haskell now. That's one of the price we pay by moving to Haskell. The code we had in Scheme to do the Merkle proofs, well, we have to rewrite it. But until it's written in Haskell, well, we have this mock-up here. And I think that's mostly it. The code is there. It's very simple. It's very hard to fake. very hard to get wrong. I'm sorry if this is Haskell code and you don't grok Haskell. Haskell is its own thing, its own way of thinking, but it's not that hard if you get into it. But what is very important to me is that this code is dead simple. Okay, maybe if you don't know Haskell, it looks a bit weird. Maybe weird is fine. Weird it just means you're not used to it. But the fact that it fits in so few lines and that the architecture to me is beautiful. Like it's there's not one thing that shouldn't be there. And that's why it will be very easy for whoever audits it to say, yes, this code is obviously right. And this is what I care about. Not being hacked, not having you get hacked, not us being hacked, not making you lose money and make us lose money because we make other people lose money. So making things super simple, correct by construction is the ideal that we're seeking. And okay, so that's what I want to say. And there's a lot of boilerplate. It's Plutus, but not that much. Like it's still pretty good, I think.
Thank you so much, Fare. Do you have any other piece of code to show? Well, that was a big update, actually. I thought it would take 5 minutes to do that. So, and cool.
We can talk about the rest, but this is what I want to show this week. Next week, we can hopefully show you more on the node side, so the contract side, or maybe we can show you on the contract side how we change this mock-up of the Merkle proof by an actual Merkle proof like we had in Scheme, but this time that will work the same by construction in Scheme and in Haskell and in Plutus. The problem with this code we had in Scheme, we had to write it in Plutus anyway. So anyway, since we need to write it anyway, we may as well embrace the whole thing and move to Haskell. So it's okay. We had the code is not lost. The experience, the understanding is there. The code we had in Scheme was so beautiful and using concepts that will fit, I think, perfectly in Haskell. So I can choose the Scheme code for the Merkle proof and how it's beautiful, but hopefully, okay.
If you still have the juice, the community wants to do that, and we also have a lot more to show every week now because we have 3 devs plus 1 part-time, so
yes,
plus you, so that's quite a lot.
Okay, so the code. The code is in actually 2 parts, and that's what I find modular and wonderful. There is more parts. So there is first a part that's generic OO definition for what a table is. And it's OO, but it fits very well with a Haskell type class. It can be directly translated into Haskell type classes, so that's very fine. So this is a generic way of expressing what it means to be a table and generic accessors for tables. So basically, it means that from these basic primitives, I can automatically define a lot of other primitives automatically. So I have a type for the key, a type for the value. I can tell you what is an empty table, how to add a key value pair to a table, how to reference the value associated to a key, if any, how to remove a key from a table, and how to fold it basically automatically accumulate something like walk over the entire table and accumulating as you do, and fold one way and the other. And if you have all these primitives and only these primitives, you can already define a whole lot of things about your table. So you can automatically deduce how to validate a thing, how to check if it's empty, etc. So you have lots of methods that are automatically defined, how to search the tree, etc., or the table just by the primitive I talked to being defined, how to join, how to conclude union. And maybe these algorithms will not be optimal for your given tree, and that's why you can override them. That's the whole principle of object orientation and to a point type classes, that you can write something that's generic, that works in all the cases, and then you can override it with something that works better and more efficiently in your case. And then that's what we do when you define the try. wait, try here, try, yes, okay. And so we are going to overwrite define plenty of the structure of a try. So this is a Patricia, a big Indian Patricia tree or try, TRIE. And there are many variants of try. I mean, there's a general idea and then there's the specifics. In the specifics of my implementation, I have either an empty try or a leaf try or a branch try or an optimization, a skip try that skips some bits of the thing. I know that for instance, on the Haskell implementation that we're modifying, they merge the skip information into each branch information. So everything is both a branch and a skip of what's to the left, or a leaf is a skip of it. So someone is calling me just at the wrong moment. Let me turn this off. Do not disturb. Sorry, I had to turn off my phone. Apologies, I had to turn off my phone. Yes, so the details may vary, but the thing that is interesting is that here I'm defining basically the control of a type class for a try, and the magic in my definition is this notion of wrapper. That is, every time you recurse, instead of saying the try is made of left or let's say something that's to the left or to the right. No, I will wrap the thing to the left and wrap the thing that is on the right, and that's where the magic happens. The magic happens that the fact that this wrapper can do the Merkleization for you and do a lot of things for you. And if you didn't have this wrapper, you would have to rewrite every time you need, oh, I want to try, or I want a Merkle try, or I want something else. And every time you would have to rewrite a new data structure. But because you have this wrapper, this idea of this wrapper where every value that you recurse over is wrapped, that's where it makes a lot of magic happen. And so the rest of the implementation is there's a lot of it is like what you expect, but the other thing that we make that's magic is using the notion of zippers. And actually, I have an article somewhere on the docs called TryZip. It's don't zip it all the way up. I invite you to, if you're interested in algorithms, to read this article I wrote. It's in the, I can leave probably the pointers, the link somewhere on the video. I will leave the link, you can click it. But this is explains all the tricks we use in our implementation of tries. And it's beautiful. I don't have time to explain it all, but it's beautiful, and it allows us to be 10 times faster than other algorithms, more naive algorithms, more like textbook algorithms for regular operations. So, like we gain a factor log n. Basically, we make things like in amortized O of 1 time, where most of people are O of log n time. So if you have things order of millions, it will be 10 times faster. And so we use this zipper thing, and that's this main magic. But otherwise, you can see where we defined a lot of empty. Is it empty? What is the height of a try? We define it's like object-oriented programming. You define lots of methods. And once again, here it's Scheme instead of Haskell. You may not be familiar with Scheme. That's just details and getting familiar with it. But what I mean to say really is that it's just like object-oriented programming. You define a base case or a general structure, and then you refine it to add a lot of details. But you only need to add the details where the details are needed. You can share a lot of the structure from what was defined before in a generic way. And you can reuse a lot of code by using some smart techniques. And here the two smart techniques I'm using is this notion of wrapper, 1, and 2, the zipper approach. And then you can see where it pays, because this does tries. There's no Merkleization, it just tries. Like nowhere in this thing is Merkleization even mentioned, except in the fact that we're using this wrapper. And so to define Merkleization, ta-da, we just need to define the wrapper as something that basically digests the try. So digest the try is a thing that digest the try is just it's basically what you will use for the Merkle proof, and you replace every node of the try by its hash, and that's beautiful. And then something like a Merkle proof in this. So now to add Merkleization, the entire file is 70 lines of code, because that's very little. And the proof validation is computing the Merkle proof is just this thing, like it's using zippers and wrappers, like it's 3 lines computing the Merkle proof, and validating the Merkle proof is like less than 10 lines of code. So by having used the right conceptual tools, you make things really simple, and which means much less code, much less places for things to go wrong or to be hacked. It's much less code, like compared to the Go code, the reference implementation of Merkle tries in Ethereum. We can implement the same thing in 1/10 of the code, and having twice the functionality, and having Merkle proofs for free and other things for free that you absolutely don't have in Go. Plus lots of tests that they don't have either. Like we have an extensive test suite. So really, they also have a test suite, but I think ours does more. And so yes, you can have 1/10 of the code do twice the job if you use the right concepts. And here are the right concepts that you have the concept of Merkle try, but everyone knows that. But our right concepts here are the concept of wrappers around recursive data structure and zippers. And so it's technical. You could think it's technical mumbo jumbo, but what is interesting is not the mumbo jumbo or the name we give to that. What is interesting is the fact that if you apply the right concept, you can make things much more efficient and much more simple. But this is a kind of efficiency you won't get by going to the low level. I mean, you can also get efficiency by going to the low level, but you need to get first big picture things, and then you can try to optimize the hell out of it at the low level. But if you just ask a low level guy to optimize things, he can extract the low level optimizations, but he will get the algorithm that is 10 times slower by construction. So he gets you code that is 3 times faster or even 10 times faster by going low level, but he misses 10x at the high level. And we can also get the low level. We can hire the low level guy afterwards, after we and get the 10x from the high level and the 10x from the low level, and then we'll have 100x. Okay, so that's what I wanted to say about this try library, and we're going to rewrite it in Haskell. That's fine. In Scheme, it was like 1,000 lines here, 1,000 lines for the try itself, 70 lines to Merkleize it, plus things that are not specific to tries. So it's not a lot of code. It's beautiful. It's simple, and yep. Anyway, okay, that's all I have for today. That's already a lot.
Sorry, my mic was muted, and so I was saying yes, that's very cool, because I also know that we have quite a lot more to show. So that'll be for next week's update, because we try to keep that edible and 34
Yeah.
minutes of code is already big. And that's pretty cool because we still have a lot to say about the Gossip Protocol and a few other things that we're upload. No worries.
Okay.
We're
Okay.
showing that next week. That's already committed. So if some people, out of curiosity, go to our GitHub, you will of course see that one of the developers, Hideo, has put that Gossip Protocol online, and that's pretty cool. But
Ooh.
you only have 24 hours in a day, so every time we make a video, that's sometime we're not
Uh,
allocating something else. Yes.
I'll bring the hopes down. She just started working the Gossip protocol. So yes, she has posted things, but it's only a start. We don't have a working Gossip protocol yet. We're just started working on it for earnest. Like before, we're focusing on the contract and the node code, but the node code in a more centralized way, like getting the basic functionality right. Now we started working in earnest on making things more distributed and more decentralized in the sense of we have many nodes talking to each other. And that's what the Gossip protocol is about. It's about how the many nodes talk each other in a way that has all the right property for a decentralized network. Because
That's great. Thank you so much, Fareh. And it makes me think that in our next mutual knowledge episode, I would love to have you can stop sharing your screen now. And yeah, in our next mutual knowledge podcast, I would love to interview you about data availability attacks because that would be fascinating
ooh,
for people.
well,
We could
yes.
have a tech talk and maybe invite a few people about that. That would be very fun.
Yeah, it's yes, it's a very interesting topic, and it's a topic that justifies having a data availability network. So yes, we need to talk about data availability attacks at some
All
point.
righty. Thank you, everyone. This was I thought it would be a trivial code update, but as I said in the previous video, we thought we could fuse that, and actually that was 1 hour of update, and we have more to show actually. So stay tuned. Next week is going to be trivial in terms of code updates, not because we don't have much to say, but because as we said, there are a few pieces of tech that will be complete in 2 3 weeks. So we're going to show it when it works completely. So far, we are on schedule. We wanted to do our testnet at the end of 2024, but because we took time to set up the companies and so on, we had that in Q1 2025 instead. So far, we are on schedule. There might be unforeseen things, but we're pretty good, and we are also on time with the Catalyst milestones for the previous edition. So we have a Catalyst 13 proposal that is live, and it's the voting period these days. So everyone, please support us, vote for us, help us get more ADA flowing in order to buy cool stuff. Cheers, everyone. Bye, Fare.
Ciao. Thank you.